question is about the depression in the freezing point. First, we'll understand a depression in the freezing point. It is also a colligative property. And the property, what is the definition of the colligative property? It is a property which depends upon the number of the solute particles, right? So, depression in freezing point is one of the quantity like that. So, what we'll do is we'll take this. This is solvent. Let's take this solvent. Solvent means single component. This is solvent, right? This is solvent. We'll use this color. This color is good. This is solvent. Let's consider this is to be water, right? It will have freezing point. What is the freezing point of water? You will say 0 degrees Celsius. Very much correct. Which is also is equal to what? 273 approximately. 0.15 is there. 273 Kelvin. Now what will happen is that it is 0 degree, no? 0 degree. This is what the freezing point is. You add what non-volatile solute. You add non-volatile solute to this. You are adding a solute. What is this? This was a solvent. This was solvent. Now, after adding non-volatile solute, what will happen? It will become solution. Now, this will become solution. So, what would be a freezing point of this? Freezing point for this will be less than 273.15 Kelvin, means it is less than 0 degree Celsius. It is 0 degree Celsius. Means after addition of the non-volatile solid to this, a freezing point of solution will fall after adding non-volatile solute to solvent. Freezing point of solution will fall. It will be less, right? Let's understand this graphically. So here, let's draw this graph. Okay, graph is this way. This axis tells you about the vapor pressure, and this is the graph about the temperature. And what happens in this case is that, let's say, freezing point. What is the meaning of the freezing point? Let's do it for the solvent. Let's do it for the solvent. Let's say this is the solvent component. Okay, this is solvent graph for the solvent. So as you decrease the temperature, means this is something higher temperature. As you keep on decreasing the temperature, what will happen? The vapor pressure will keep on falling, and it will fall so much that it will change its state. This is frozen. Okay, this graph, I'll still draw better. Let's do this. This is this is for the solvent. Means at this higher temperature, obviously it will have higher vapor pressure. And as you decreases the temperature, vapor pressure of the solvent will keep on falling because this axis is of the vapor pressure, right? So it will fall so much. One point will come, one temperature will come so much that molecular motions will be very, very less, and um, solvent will freeze. Solvent will change its state. So this is solid. Solvent will change its states. So this is a graph where the this is the temperature you will call TF. This temperature you will call to be is equal to T naught F. This is T naught F. Means not means pure evaporation, right? And the graph which I'm going to draw for the solution is this. You can start from here, here, anywhere, but for solution it is this. Means after addition of the non-volatile solute, this has changed what? Now you will not call that to be a solvent, no, you will call that to be a solution. And this is the temperature at which solution will freeze. This is the temperature at which solution will freeze. This this part is called frozen solvent. This part is called frozen solvent. And this another curve which is there, it is a this curve is called frozen solution. So this is the point where the solution is freezing. So this I'll call TF, and this difference I'll call delta TF. So this delta TF will be more if you are adding a more amount of the solute. Means delta TF is directly proportional to molality. So delta TF is equal to KF into molality, right? We write this to be, there is one more factor, that is Vent of factor I, right? Since it is a glucose, there is no any dissociation or the association, so I factor is 1 over here. So I factor is 1. So this is what the molality and the delta TF and F. So we'll derive the further formula from this. Delta TF is equal to KF molality, it is right, molality, molal, right? So it is number of moles of solute upon weight of number of moles of solute upon mass of solvent in kg. This 1000 is a conversion factor because whatever weights you are given, you will be writing that in grams over here, right? And this is a conversion factor. So further, I can write this delta TF is equal to delta TF is equal to KF. NB could be written as a WB MB. Why? Number of moles is given weight upon molar mass into WA into 1000. This will just give you a delta TF. Remember, this will just give you a delta TF. Let's take this here. Okay, I require this space. So delta TF. So WB is given weight of the solute is, let's calculate delta TF. Let's calculate delta TF. Therefore, delta TF. KF is given to be 1.86. Weight of the solute, WB is the weight of the solute, 1.05. Molar mass of the solute, it is glucose, no, 180. 180 is the molar mass of the glucose, right? How we calculate, we know, like combining the atomic mass of C6H12O6, combining integral multiple of all these atoms is the molar mass. Then 1 by WA. What is the mass of the solvent? 160 gram of water. So this is equal to 1000 over here. So what would be the value of delta TF? Delta TF, 1 minute, student. Okay, let's continue. I just had a call over here. So this is what the delta TF is. Let's calculate that. That is equal to 1.86 1.86 multiplied by 1.05 multiplied by 1000 divided by 180 divided by 160. So delta TF, what I am getting, difference is 0.0678. Yeah, this could be approximated. Delta TF 0.068. Let's approximate it. So you are told, question was not about a depression in the freezing point. You are told to calculate the freezing point of the solution. So what is this delta TF? It is uh, T naught F minus TF, which is equal to 0.068 Kelvin. This will be in Kelvin. Okay. So what is the freezing point of the solvent? T naught F is the freezing point of the solvent. I'll define this. This is T naught F is freezing point of solvent, and TF is freezing point of solution. Yes, no, that's what exactly. Yeah, freezing point of the solution we need to find. So T naught F is a freezing point. So how much is the freezing point of the water? Water was a solvent. So 0 degree. 0 degree means it is 273.15 Kelvin minus TF, which is equal to 0.068. Therefore, TF is equal to 273.15 minus 0.068. So answer comes to the freezing point of the solution to be is equal to 273.082. So earlier it was freezing at 273 Kelvin, 0.15. It has decreased to 273.082. So that's what the depression in the freezing point is. Let's solve this question. This question is about the osmosis and the osmotic pressure. Before we understand this question, let's have a look on the concept of the osmosis and the osmotic pressure. Osmotic pressure, let's draw the setup first. Uh, this is what the one chamber, and this is another chamber where there will be a solvent. Here, what I'll do is, okay. So osmosis and the osmotic pressure. Let's understand this. there is some there is a lead, a frictionless lead. We'll consider this as a frictionless lead. Here there is a solvent, here there is a solvent, and this is solution. Or we'll do this way. We'll do it this way. This is solution. This is solution, and this is solvent. Understand the difference. Understand the difference that what does it mean? Uh, there are two ways to express. Uh, Here, this is a solution. Here, there is a semi-permeable membrane. What is osmosis? Osmosis definition. We'll stick to this definition. Osmosis, by definition, is a movement. It is movement of solute. Sorry, it is movement of the solvent molecules towards It is a movement of the solvent molecules. 1 minute. What's this happening? Yeah, computer got hang in between. Movement of the solvent molecules from high concentration to low concentration through semi-permeable membrane. Okay, this SPM is also called as SPM. Semi-permeable means membrane means SPM, semi-permeable membrane. Right. Let's understand this definition. Movement of the solvent molecules from a high concentration to the low concentration. Now, if I ask you one question, what is the concentration of the solution? Where the concentration of the solution is high, I'll write two things over here. One will say, one I will write a concentration of the solution in terms of this. I'll write here concentration of solution. Where it is high, since it is a solution, here it is high, and concentration of solution is zero. In the case of solvent, there is zero concentration. Why? Because this said there is no solute. So concentration of the solution I am asking. Like how much of the solute present in that case. So here it is high, here it is zero. But if I say same question, concentration of solvent. Here, concentration of the solvent is more. We can say that concentration of the solvent is more, and here concentration of the solvent is less. Why? In a same amount of the quantity, there is a solvent plus solute. So here there will be less amount of the solvent, and here there is more amount of the solvent. So movement of the solvent in this direction is called as osmosis, from higher concentration to lower concentration. So understand the difference. Concentration of solution is less or zero over here, but concentration of solvent is more in the side of the solvent and less in the side of the solution. That is what the osmosis. And if this solvent is moving in this direction through a semi-permeable membrane, then what's going to happen in this direction? If it is moving, then what's going to happen is that this lead is going to go up, right? This lead is going to go up, and the pressure required to just stop this osmosis, minimum pressure, that is called as osmotic pressure. So this is the idea about this. Means more is the concentration of the solution, more is the concentration of the solution, more solvent will move. The difference of the concentration of the solvent in both the chamber will be more. So more is the concentration of the solution, more solvent will move in this direction, right? So here that osmotic pressure pi is directly proportional to concentration of the solution. This C is the concentration of the solution, and R and T are the constant. And there will be a Van 't Hoff factor I. For the non-electrolyte solution, I is equal to 1. Okay, let's solve this problem. Um, let's solve this problem. Based on osmotic pressure. As we know what is osmotic pressure, uh, we'll understand this. We'll understand this. So a question asked is solution containing 15 gram of urea per liter of solution in water has the same osmotic pressure as the solution of glucose in water. Calculate the mass of glucose present in a 1 liter of solution. See, the thing over here is, let's start with this. Pi is equal to what? Osmotic pressure is given as pi is equal to CRT into I. I is a Vent-Off factor. If it is a non-electrolyte solution, then Vent-Off factor will become what? Vent-Off factor will become 1. But glucose is what? Urea and glucose both are non-electrolytes. So formula will change to what? Pi is equal to CRT because I is 1. Now, what they are saying is that a solution containing 15 gram of urea per liter of solution in water has a osmotic pressure as a glucose in water. Okay, glucose in water. Calculate mass of glucose present in 1 liter of its solution. Means let's discuss for the urea. Urea, what is osmotic pressure? Uh, if it is a urea, it is what? Let's consider this pi 1 to be is equal to C1 R T. So pi 1, what is concentration? Number of moles of solute, that is number of moles of B. It is concentration of the solution. No? C is the concentration of the solution, right? C is concentration of solution, remember. And R is a gas constant. R is gas constant. And T is temperature at which this process is happening. T is temperature. So concentration is the number of moles of solute upon volume of solution in liter into RT. See, volume we many times write in ml. So 1000 will be a conversion factor. If you're writing that ml, so that will be a conversion factor. We'll be writing that in it's converted. Okay, volume will be converted over here. This is about this thing. So I will still write this pi 1 number of moles of solute written as WB upon MB into 1 by V RT into 1000. First we'll form two equations. First we'll form two equations and then we'll decide. I'll take this on the top, this window. Yes. I'll discuss about a pi 2, that is osmotic pressure 2 due to a glucose. So it is also C2RT because gas constant is not going to vary, right? So um, that will be is equal to that will be is equal to same. It will be same. Temperature is also same for both the things, right? So here, what would be a pi 2? Pi 2 will be number of moles of B. Now, number of moles of B, instead of writing a B, what I'll write is that number of mole will change this slightly because here also writing a B won't, it will lead to a small confusion. So we'll write U for a urea. It is U, no? Number of moles of U. This is weight of U and this is molar mass of U. Here this is concentration of urea solution. U will be a concentration of urea solution. And here also I'll change this pi osmotic pressure U U U. This is due to urea, and this is due to glucose. So for this I'll write osmotic pressure due to glucose G. This is G and this is also G. Number of moles of G upon volume into R into T, and this 1000 is multiplying factor, right? Conversion factor. So pi G will be is equal to what? Number of moles of G is what? Weight of glucose taken upon molar mass of glucose into RT into 1000, right? But what they have said in the question is that they both have same osmotic pressure. It is mentioned here, right? That per liter of solution in water has a same osmotic pressure as a solution of the glucose in water. Both are having a same osmotic pressure. Means over here, what I can say is that what we can say here is that pi urea is equal to pi glucose. Means what is pi urea? If I write from here, if I write from here, or I'll take it here. Pi urea, pi urea is equal to pi glucose will be is equal to what? Weight of urea upon molar mass of urea into 1 by V RT into 1000 is equal to what? Weight of glucose upon molar mass of glucose into RT into 1000. So this 1000, RT, RT, 1 by V is there. Okay. Volume is also same, no? Volume is also same. Per liter of the solution, here also glucose is in 1 liter of solution. So this volume will also get cancelled. What remains is VU, molar mass of U, weight of glucose, and molar mass of glucose. What you are told to find in a question, calculate a mass of glucose present in 1 liter of solution. So this is what we need to find. So if we rearrange that equation, what would be that? It will be weight of urea multiplied by mass of glucose, right? Divided by molar mass of urea. What is the weight of urea given? 15 gram. What is molar mass of glucose? It is 180, 180. And what is molar mass of urea? 60. It is 60. 6 threes are. So weight of glucose in gram is 45 grams, and that's it.